Hey, what's up, guys? This is Cheng here. So this time LeetCode number 1937, maximum number of points with cost. Okay, so you're given like I'm by n integer matrix, right? Points, and we want to maximize the number of points we can get from the matrix. So the way we're getting the points is that we will pick each one cell. Basically, we'll pick one cell in each row. Okay, and after that we'll get the points, right, of this row and column. But there's a cost. So what is the cost? Basically, the cost will be after picking the difference between the column of two rows. So which means that if you, for example, there's like this cell, right? If you pick this one, right? This one, you pick this one, and then the second time, let's say you pick this one, then of course you'll get both of the points in the cell. But since the column difference is what, as you guys can see, it's this one, right? So there's 0, 1, 2. So there will be P1, right, plus P2 minus 2 in this case. Okay, assuming this is one P1, this is P2, right? So that's basically the cost. And our task is to find the maximum number of points we can get, right? For example, we have this 3 by 3 grid here, a matrix. So the answer is 9 because 3 5 3 5 3, right? And the column difference is between these two is 1, and between the third and second column, third and second row is also 1. That's why 11 minus 2 will be 9, right? And here's another example, right? And there are some constraints, right? So both mn is 10 to the power of 5, and also m times n in total is also 10 to the power of 5, right? So, I mean, for this one, obviously, this one is a DP problem, right? And I guess most of people can at least get the first solution. Not It's not a solution because it will TLE, which is the we define DP I and J, right? So DP I and J means that the maximum, right? The maximum points we can get. The maximum point we can get, right? Uh, ending, right? Ending at this I and J, right? So if we define the DP in this way, right? Um, so how can we update? How can we write the state transition function, right? I mean, obviously the brute force way is like what? It's like this. So basically we have this row, right? We have this row here, and we have this is a previous row, right? So this is a previous row. Let's say this is I and J, right? So this is I, and this is J. This is I minus 1. Okay, right? So let's say we're trying to get the maximum point for this cell, right? So the first approach is that obviously, we just simply loop through everything from the previous DP, right? Because from the previous DP, we want to check each of the cell, right? We want to check each of the cell, and then we want to see from that cell to here what's going to be what's going to be the point we can get, right? And after that, it's going to be a DP of what? So basically DP I and J, right, equals to the maximum, right? The maximum of what? Of the DP I minus 1 and then K, right? Uh, Here we have to subtract the absolute difference between the K minus J, right? So that's gonna be the first DP transition function, right? Where we have to check each of the previous element from the previous DP state, right? And then we compare, okay, which one can give us the biggest one, right? To the current one. But as you guys can see, right? So to loop through everything, so basically, so the time complexity for this one is what? So we have to go to m rows, right? We have m row, and for each row, right? Sorry, yeah, for each row we have to populate n columns, and for each column we have to loop through the previous the entire previous row, which is going to be what? N square, right? So this is going to be the time complexity for this one. But remember, m times n equals to 10 to the power of 5, and n is also to the 10 to the power of 5, right? So with this one, it will TLE, right? That's why we have to come up with some improvements. So what's going to be the improvements? So if you watch this one closer, obviously, the path, right? So the optimal path for this I and j either comes from left or come from right or coming down below here, right? Or from the cell above him, or from the left, or from the right, right? And so basically, in this case, we can use another DP concept to calculate the entire row. Instead of looping through, for each of the cell, we loop through the previous row again. So how can we do it? Let me draw another. Let's say we have a DP. This is DP, right? I minus one, right? So let's say we have like this. I will just draw a few. And this is DPI, right? They have the same cell column, right? So let's say this is the one we're trying to get. Okay, so this is the J, right? And from left, okay, so let's only consider the left side. Okay, so we have what? So let's call this one. I'll call it P0, right? It's not. I'll call it what? So this is gonna actually the DP, right? So let's call it D1, D0, right? D1, D2, D3, D4, and D5, right? So from the left, okay. So for this DPJ, right? So for DP I and J, right? So from the left side, it's going to be the maximum of what? Maximum of, as you guys can see, we have D0, we have D0 minus what? Minus 5, right? And then D1 minus 4, right? D2 minus 3, D you know what? Let's do this J, so we can write some shorter codes here. D1, okay, so this is going to be D0 minus 4, D1 minus 3, right? And D2 minus 2, right? D3 minus 1, and then D4 itself, right? So that's the max value we can get from the left side, right? Right. Now how about the J minus one here? How about this one? So if we dp of I J minus one, right? So what's the what's the value for this one from the left? Similarly, we have max. It's going to be D0 minus 3 in this case, right? And then D1 minus 2, D2 minus 1, and then D3, right? So this is the DP of j minus 1. I think you guys already see a pattern here, right? So see this part and this part, they're exactly the same, and except for what? If we use this one, the dp ij minus 1, do a minus 1 of this one, we get the dp ij, right? Right. So that's why, if we calculate, as you guys can see, right? So if we calculate the new dp from left to right, right? We don't have to compare everything for the previous row. All we need to compare is the one above us, right? And the ones on the left, and then we do a minus 1 for the ones on the left. Basically, these two, right? So which means we only need to compare two things. Now we have what? We have dp of I, j, right? This is going to be what? Max of what? Max of dp I, j minus 1 minus 1. And then what? And then the dp I minus 1 j, right? So now we have this state transition function. So this is the one, this one from the left, right? This, because we can use this one to give us everything we need, right? For this part. And then the last one is this part, which is this one, right? So now, as you guys can see, instead of n square to check the new row, we only need n, O of n, because one more thing, we need to do this twice, right? One time, the first time we scan it from left to right to get everything from the left side, and then the next one we scan from right to left, because because the optimal path could come from the left or coming from the right, right? And then we get between the left and the right one, we get the bigger one, and then we use that one to populate the current DP. Yep. So I think that's it, right? I guess then we can start coding, right? We have this one point m and n, right? Point, okay. And then for DP, since we only need the previous one row of DP, so we can just compress the space complexity into one-dimensional DP, right? Which means we only need the DP to store the previous row's result, right? So at the beginning, it's this one, right? Because for the first row, right, there's no cost, right? So so the DP value is the first row of the point, okay? And then I'm going to define the left and right. Okay, so for the left and the right, okay. So basically, this left and right means that the biggest one we can inherit, we can get from left side or from the right side, okay. And then for I in range of 1 to m, right? So first we scan from left to right, which is while j in range of n, right? So if j is equal to 0, right, then we simply do a left dot j equals to dpj, right? Because for the first one, there's nothing on the left, right? Else we do a left j equals to the max of left, like j minus 1, right? And then minus 1, and then dpj, right? Yeah, okay, so remember, so before, when I draw the diagram, I use dp I j minus 1 here, right? I think we can use the same thing, but here I just separate this one into two DP array here, just to make this code more much clearer, right? So here we have two DP array here, one for the left from left to right, and the other one is from for the right to left. Okay, right. And then the next for loop is for the right one. Okay, it's going to be n minus 1 minus 1 minus 1, right? So this time, similarly, if j is equal to n minus 1, right, then we have right of j equals to dp of j, right? Else right j equals to the max of this time it's going to be right of j plus 1, right? And then also do a minus 1, right, of dp j. Okay, so yeah, this part is pretty obvious, right? Because even from the right side, so every time we also need to do a minus 1 because the difference, right, it will always be increasing by 1 from the neighbor, right? Okay, and then the last for loop will be like this, right? Simple. We just need to do this. dpj, right? So now this time the dpj will be what? It will be the point, right, of the current one, which is I and j, plus what? Plus the bigger one, right, from either the left or the right, right? So this one, right j. Okay, and then in the end, we simply return the max of dp. So I think that's it, right? If I run the code, okay, accept it, right? And there you go, right? Because obviously this one is what? The time complexity for this one, the first is the m, right? And then we have another n here, time m times n, right? Yeah, I think that's it, right? I mean, this one, I think it's a little bit tricky. I think the first one is pretty easy, pretty straightforward, where like, for each of the cell, we loop through everything from the previous row, right? And then we try to get the maximum from it. But it turns out we don't have to do it we don't have to loop through the entire previous row for each of the cell. Instead, we can use another like DP concept for here. This one actually, I think it's similar. I remember there's like a problem called trap raining water, right? I think for that one we also use something similarly for this one. I think for that one we also use define like a left and right DP, and then we populate the left and right, and then we choose which one is bigger, right? In the end. So similarly for this one, right? Because I think I already showed you guys why we can make this transition, right? Because this one includes everything for the current row, except we have to do a minus one, right? And yeah, I think that's it for this problem. And thank you for watching this video, guys. And stay tuned. See you guys soon. Bye bye.